present to you about an investigation on the one-way speed of light. Now, time for some context. In Einstein's 1905 paper on the electrodynamics of moving bodies, there was actually a postulate, which is that we establish by definition that the time required by light to travel from A to B equals the time it requires to travel from B to A. And this was also written in the definition of c, where c is actually the two-way speed of light, and it is twice the distance AB over the amount of time it takes from A to get to B and then back. And on the one-way speed of light, of course, it is the thing we're actually discussing about in this presentation. And Derek Muller, or better known as Veritasium, has already stated the quantity to be impossible to measure due to the impossibility of constructing synchronized clocks without assuming anything about the one-way speed of light to begin with. And thus, the thought experiment outlined in this presentation aims to provide a method of testing this claim. Now, we look at a comparison, right? So in the first case, we have a constancy, which is that it takes the same amount of time for light to travel from A to B, that is, and compared to travel from B to A. Now, in this case, the one-way speed of light is c, and this is nothing special. This is what's assumed in Einstein's paper. And the more interesting case is that what if it's not? Like this diagram is also already adapted from Veritasium, and this extreme case is that light takes twice as long to travel from A to B, and it comes back instantaneously from B to A. Now the thing is, how will you be able to tell the difference between all of these? Right? You can't really tell the difference. So this is what we're trying to figure out, and this is kind of the premise of my thought experiment. Now we move on to the definition, and synchronization convention fail to hold if the time taken for light to travel from A to B is not equal to the time it takes for light to travel from B to A. Therefore, for any kind of meaningful measurement of the speed of light, some form of absolute reference is required. Hence, we define absolute reference as a slice of spacetime at some agreed upon time t, where all states are measured locally. This is not against relativity. The light does not really care how you define simultaneity. It will always travel at the same speed in a given medium. Okay, I kind of lied there. We actually don't know. What if light is like slower in this area of space-time and faster in some other area? We don't actually know that, but uh, anyway, we can't really do anything about it if that's the case. Everything breaks down, and also I'm actually not very familiar with relativity. Someone should correct me if I'm wrong about this. Like if light actually does care how you define simultaneity, and it will travel at a different speed, then I apologize for actually releasing this video, because in that case, well, my entire theory falls apart. Anyway, for the theory. Since the clocks cannot be synchronized in the traditional manner of using light, a different approach is needed in the form of randomization. And suppose there exists a fixed number of radioactive nuclei, n, and they are distributed randomly. Then the probability of each atom in every position of space is identical in the absolute frame of reference. Thus, if the radon gas is evenly mixed during production, this will cause an overall absolute uniform distribution when averaged over many trials. This also means that from the perspective of each individual atom, the concentration of other similar atoms are going to increase with distance. And here, since the concentration should be constant throughout the sample at any given instant of time, uh, thus, if the light were to travel in the radon at different time slices, the light will encounter different concentration of radon atoms, and this is how we actually tell the difference. If it takes longer to travel in radon, if it takes a bit longer to travel in the radon gas, it's going to you'll actually see you'll actually see more of the light is actually going to get absorbed by the radon, and if it and vice versa, if it takes longer to get there, because at the end of the stage it's going to have fewer radon atoms than in the beginning. So therefore, the intensity measure will be slightly higher than that if light travel faster. Now here we go on to the procedure of the thought experiment. Again, I have to emphasize that this is a thought experiment. It's not really realistic, but the idea is simple. Firstly, you obtain a sample of radon with a known concentration measured at some fixed time before the experiment independently. And this is because the concentration is actually very easily measured. And also, after measuring the concentration, the way it decays is also fairly easy to predict. So therefore, you can actually know when it started and when it finished. And then you shine a laser with wavelength 351.7 nanometers through the radon gas. And the reason this wavelength is chosen is because it's actually it's an absorption line of radon, and therefore it is specifically only going to be absorbed by the radon and not by any of its decay products. And then finally, you record the intensity of the laser after arriving at the observer. Now, the main working principles of this experiment is that large number of radioactive nuclei decay at a known rate, because it's governed by probability, right? Is not something that is going to be affected by how fast the light is traveling. And radon decays into polonium over time, and polonium has a distinct absorption spectrum from radon, and this means that any decayed radon atom will not absorb the laser, and therefore it will not show up on the results. For the control, every aspect of the radon gas production must be strictly controlled to ensure a fixed initial concentration, such as the material used to produce the radon, the amount of material used to produce the radon, and the time interval between the experiment and the measurement. And additionally, due to the relativistic effects of motion on relative time, the temperature of the gas sample should be minimized where possible to avoid time dilation related systematic errors. The function of the concentration of radon with respect to time, which is sourced from IBO, I don't know where else to source this from, and it is nt equals to n0 times e to the power of negative lambda t, where n0 is the initial concentration, t is the time it takes for light to pass through the radon sample, and lambda is the decay constant. Continuing the equations, we have T equals to ln2 over lambda, where T is the half-life of the radon sample. Thus, we have lambda equals ln2 over T, and therefore Nt equals to N0 times 2 to the power of negative T over big T. Then, we use the Beer-Lambert law to find A, the absorption coefficient, where A equals to epsilon times C times L. And here, epsilon is the absorption constant, C is the concentration, and L is the length of the gas the light passed through, and A is equal to ln E over E0, where E is the measured intensity of light, and E0 is the initial energy of light. And since the concentration changes over time, we can write this as a sum of many infinitely small intervals. A equals to epsilon L times the integral of n0 times 2 to the power of negative x over t integrated with respect to x and between 0 and t. And then we have A equals to C0 epsilon LT over ln2, the entire thing, times 1 minus 2 to the power of negative t over big T. Or more simply, we have since the bunch of stuff on the left are just a bunch of constant, we have A is proportional to 1 minus 2 to the power of negative t over big T. Now here I think I have to make a very important clarification. I think I mentioned it before, but I do have to say it again. This remains a thought experiment due to how incredibly impractical this experiment is. Firstly, radon is very hard to get in sufficiently large quantities for the experiment. And also, even in the extreme case of CAB equals to infinity and CBA equals to C over 2, the time discrepancy is tiny, so you wouldn't actually see that big of a difference. And if you want to actually see a bigger difference, you will either have to use a more radioactive substance, which makes it even harder to get in sufficiently large quantities, or you have to make a longer tunnel, which is again also very impractical. Therefore, I think it should be emphasized that this experiment is highly unlikely to be conducted in practice. However, should results be obtained from such an experiment, this can prove the isotropy of spacetime that was postulated in Einstein's theory of relativity. And here are my sources. Thank you.